Okay, all right. So the today's topic is CMOS circuit design. So it's basically CMOS fundamentals, you can call it. Okay, okay. So it is one of the family of MOSFET. So before that, so when I'm sure everyone is from electronics background. And what is the first thing that you have read when you started learning about electronic devices or something? So probably, if I understand it correctly, you would have learned something like kind of wave physics, semiconductor physics. Okay, and then you might have learned, if I'm not wrong, PN junction diode, PN junction diode. Okay, and then you would have learned there is something called BJT. Okay, and then you would have learned something called MOSFET. Okay, now so when we say P-N diode, what it is it meaning? So semiconductor physics is basically what is the meaning of N type and P type and all of that. Okay, and what is when you put them together? What kind of region that is actually forming and all of that. So now, what is this P-N junction diode? What is this P-N junction diode?
Hi, sir. Am I audible?
Yeah, you are audible.
Hi. Yeah. So basically, sir, there is a three type of materials. One is insulator, conductor, and semiconductor.
Right,
So generally, semiconductors are neutral, but under some impurity addition, or if we, dope them like P type and N type, so they exhibit a specific kind of uh, phenomena. And if
right,
we join two p-n junction diode, then there is a immobile ion because the p and n combines, which we call as the depletion region.
exactly. Okay, and now coming to this P-N junction diode. So we usually say it like kind of say like this. This is the kind of symbol that we follow.
Right.
And so this is going to be kind of P and this is going to be N type. And people even, you know, say, it's kind of, they say it like this. So it is kind of, so there are two operating, modes. One is forward bias, okay, forward bias. And then the other one is reverse bias, okay. Now, so if you look at, right, what is the meaning of forward bias? So it is when you say forward bias, it is basically say 5 volt, and then the other side, it is basically kind of say lesser volt. Say this is kind of 5 volt and this is kind of say 0 volt. Now in this scenario, this diode is said to be conducting. Okay. Now this is something that we call it as a forward bias. And when I say reverse bias, now what is this meaning is, so this is basically kind of the same thing, just that the N side is going to be more supply voltage. Okay, now say this is going to be 0 volt and this is going to be kind of say 5 volt. Now when you do this way, it is kind of, we call it as a reverse bias diode. Okay, and this is it's kind of forward bias diode. Now in forward bias diode, it's kind of conducting, and you will see a kind of output here. Now when it's reverse bias diode, it is completely off condition, so it is kind of the depletion region is kind of increases, so it is more of the it's more of what do you call it, on off condition. Okay, and now remember, this basic diode you would definitely need to know. Okay, uh, how it is operates and what are the modes and all this, because there is a phenomena called, or probably one of the sign of check called antenna check. Okay, antenna check. it comes under physical verification. Okay, now so if there is something called, if there is an antenna violation, then one of the fix is to add reverse bias diode. Okay, so how that actually helps in solving your antenna violations and or antenna phenomena and etc. Okay, so the PN junction thing, just go through a basics level, okay, which would actually um, definitely you should know, being electronics engineer. Ideally, if you ask me, right, everything is kind of PN junction kind of things only. So let it be a BJT or let it be a MOSFET. So ideally speaking, right, say if this is your P-type material, okay, so this is your P-type material, and you would actually have N-type material. Okay, now, so there is a region that is kind of being formed. It is called depletion region. So this is the kind of region where, in case of forward bias, it becomes very narrow, and in case of reverse bias, it becomes bigger. Okay, so that is how it is actually working. When it is in forward bias, and when it is, it is kind of off. When you say it is a reverse bias. Okay, okay. Now the next thing. So what is this BJT? It is basically bipolar bipolar junction transistor. Bipolar junction transistor. Okay. Now in this, so this is what we would have read in our college days. Uh, so it is kind of say a three terminal device. What and all we call it here? This is
Uh,
base
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 and
emitter collector.
intercollector. That one is the collector.
Collector.
it is just, you can change it, so it's not a big deal. So collector and then emitter. Okay. Now, so what is this BJT? Is it current control device, or it is kind of, when it turns on?
It is current control
It is
device.
current control device.
So it is,
IC
there is
equal to
something
beta times
called
IB.
IB. It is kind of something called, we call it as IB. Now, when the IB is more than certain value, it kind of turns on and operates. And with this, there are different configuration. There is something called a common base, common collector, common emitter, and all of that. So, okay, let me ask you a question. So, is there anyone who is using BJT for their, for the IC design now?
No, sir.
Ideally speaking, nobody is using the BJT for the IC design at this moment. Okay, so everyone is using
The
the
MOSFET.
MOSFETs. It's basically kind of, we call it like kind of, one of the family. So in MOSFET itself, okay, we'll come to that. So BJT, now when it comes to BJT, there is a again NPN and then PNP. So there are two types of devices depending on the way, or depending on the materials that you kind of stack it. Okay, and yeah, and now moving to MOSFETs. So what is this MOSFET? What is this MOSFET?
It is a voltage control device, sir.
So it is basically similar to the same transistors. I mean BJT, but it's just that we have a different terminals, and it's basically we have, it's kind of, it's a voltage controlled device. Okay. Now it is basically a four terminal device. What are the terminals? The main thing is source, drain, and then gate. And this is something we call it as a bulk. okay, or well type, or well, okay, bulk or well, okay. Now if you look at the transistor, okay, it is kind of, there are basically two types. One is basically enhancement mode, okay, enhancement MOSFET, and second is kind of say depletion. Now what is this difference between this enhancement and depletion here? So if you look at enhancement, when you supply something, then it basically conducts, okay.
Here we creating the channel, sir. Before there is no any
so
channel between the
so
inducer.
exactly, so there was no channel before, or there was no channel by default. Now you try to create a channel and let the charges flow through it. So that type of transistor is known as enhancement MOS. Now when you say a depletion, there is a channel which is already formed, okay, and you just try to apply certain amount of voltage to turn it off, removing the channel, okay. Now so out of these two, which one the industry is using or preferring?
enhancement,
Okay, reason?
because we give external voltage to conduct, but in depletion mode, normally it will be loss will happen, but in
What
NMOS
loss? What loss? You are saying loss, but can you be more specific? What loss are we talking about it? Anyone else?
Leakage, sir.
When a transistor is on, is that leakage is going to be matter?
No.
So what is leakage? Okay, anyway, we will talk about all that. So it is basically we prefer enhancement mode, I mean enhancement mass, okay, and we don't prefer depletion because it is always on. So there is gonna be a power dissipation, okay. So your dynamic power dissipation may end up on the higher side because anything that any kind of IC that we are designing now are likely that are all are kind of power efficient ICs, okay. Either they could be operated by a battery, or even let's say for example servers, they are all kind of power hungry. So people look at mainly PPA, so it is power performance area. So the power is the first thing. So your depletion mode mass, there are chances that you may see a more power consumption, okay. And now coming to the types of MOSFETs, what are the different types here? What are the different types? So, okay, if you look at, there are two types. One is NMOS, okay, and another one is kind of say PMOS. So NMOS, okay, so it is manufactured on the P substrate, whereas PMOS is manufactured on the N well. Okay, I'll explain you how the cross sections and all of that. Okay, so there are two types of MOS. In within enhancement, under the enhancement, there is something called NMOS and then PMOS. Okay, now so why do we call this MOSFET? So what is this actually? When we say P-type body, what it is? So it is basically silicon. Okay, it is basically silicon, and then you have, after the silicon you have something called this is oxide, gate oxide, okay, oxide, gate oxide. And this gate initially it was kind of say metal, okay, metal oxide semiconductor, Okay, so that is the name, how that is how it got the name. Okay, so the gate is basically a metal, and then you have got your oxide, and then you have got your silicon substrate, which is basically the semiconductor. Okay, so that is how the name came into picture. Okay, and when we say a transistor, right, MOSFET, now we discussed about four terminals. So this is basically a gate. Okay, and say there is a source, and then say there is a drain. Okay, now if you look at the way the cross section, so look at this way. Now say this is your schematic. Okay, now tilt the schematic as kind of something like this. Okay, now when you tilt it, what actually happens is it is going to be say something like this. It is going to be say something like this. Okay, so this is basically, you call it like kind of source, and this is, we call it kind of drain, and then this is, we call it kind of gate. Okay, now this whole thing is kind of manufactured on the uh, silicon substrate. Okay, now, so we know what is this, what we have a gate, source, drain, right? And the fourth one, we always say it like this. So it is kind of bulk. Okay, it's kind of bulk or weld connection. Okay, or weld tap connection. Okay, now your source is the main terminal where you kind of either connected to VDD or VSS, depending on your circuit requirement. And gate is the terminal which controls the flow of charge, which controls the flow of charge. And drain is the terminal which is kind of controlled. It's a controlled terminal. Okay, so when you turn on the transistor, your drain gets charged. Okay, or the drain get discharged depending on your source potential. Okay, now, so this is a kind of cross sectional diagram. Okay, this is a kind of cross sectional diagram where your silicon substrate is something that we call it as a kind of the body, and on top of it, then you go and add n type impurities or doping, and then you kind of name it as source, and then drain, and then you go and do the oxide, that is a gate oxide. Okay, and then on top of it, the gate material. Now there are different material that we have, hafnium and then high K and all of that, but the initial time we were kind of using the metal. Okay, now when it comes to any kind of transistor, right, so there are two parameters that is really important. So there is something called width and length. So what is this width and length? So if you look at when I say gate, okay, when I say a gate, it is basically the length of the transistor. So I mentioned W and L. Okay, it is basically the length of the transistor. It is basically the distance between your source and then your drain. Okay, source and drain, and your gate, the length, when you say poly length, is nothing but your transistor length. Okay, now the technology, when we say the technology, so it is kind of say 28 nanometer or 40 nanometer. Okay, now what is this meaning is the distance between the source and the drain is basically 0.028. micron, or okay, 0.04 micron. Okay, now people also have 16 nanometer and etc. So 0.016 nanometer. Okay, now this is the one which defines your technology. Okay, this is the one which defines your technology. And now what is this W? Now, if you look at this, is a kind of the 3D kind of section, 3D kind of structure, where this is your front post, the cross sectional, and this is a kind of the the width. So now this is kind of the, now this is something that we call it as a width. Now, so the simple thing that I can give you is, say for example, you are actually going through, going on a road. Now, say there is a small bridge that is kind of constructed. Okay, there is a small bridge that is kind of constructed. Now, so this, the size of the bridge, that is called length, and the width, it is called width of the bridge. Okay, so you have to assume it like this so that you won't forget any time. Okay, now L and W are two important parameters for any kind of transistor. Okay, now, so let's get into more detail on this W and L now. So what is propagation delay? What is delay?
The time taken by the input signal to change its value and produce output values.
Okay, now, so everyone knows about, I think you guys would have heard about what is something called propagation delay and all of that, etc., etc., and all that. Now, the important thing is, now the delay depends on what parameters? The transistor. So it's basically, ideally speaking, right? Your source. So the way I look at is, say this is your source and say this is your drain. Now say there is a cap, load capacitance. I'll explain you what it is. Now charging and discharging. So charging this cap. Now how much time does it take to charge? Okay, and it depends on what parameters. Okay, so I'm talking about just a pure transistor level. Okay, now remember this, your L. So when L reduces, what happens? What happens to your delay?
Decrease, sir.
Decreases.
Huh?
Decreases.
Okay, delay
Decreases.
decreases. Now that is the main reason we always go and target the lower node. Okay, so say a cell in 40 nanometers. So let's take buff X8. Okay, buff X8 cell. So in 40 nanometer, this might give you kind of, say, 30 ps. Now in the same cell in 28 nanometer might give you 25 ps delay. Now the same cell in 16 nanometer might give you approximately 20 ps. Now what is this meaning here? So when we go down the technology, what actually happens?
The delay is decreasing, sir.
No, I'm not asking about the delay. I mean, in terms of structure.
The length will be reducing, sir. The
So
distance
the
between source and
length
drain.
between the source and the drain would be kind of reduced. So this is kind of keep getting reduced. Okay, this is the main reason your delay is kind of getting reduced. Okay, that is the main reason we keep advancing, or probably keep going through the latest nodes and then see if we can actually make the performance better and etc. Okay. Now coming to something called width. So now what is the relation between your width and your delay? What is the difference? What is the relation between width and the delay?
If width decreases, the delay increases.
If width decreases, the delay increases.
Increase.
Okay. Can you justify more how it is?
The channel width reduces for the current to pass. So that's why it
Oh,
takes a long time.
okay. Okay. So let me give you a simple example. Now, say you have there's a kind of road which is kind of say two people, two-lane road. Okay. So two-lane road. Okay. Now you make this as a single lane road. Now what happens to your traffic? Your traffic increases. Correct. See, this is kind of two-lane road. Now your two-lane road. Now you reduce it. Now what happens to the number of the vehicles that is going through that way?
More,
It
sir.
is it is kind of same. Assuming the same kind of number of vehicles. Now what will happen is here because of you have less road now, the road size is lesser, so you might end up in seeing more delay. So the same thing happens now when it comes to your area where it's kind of traveling. So it is kind of it has kind of the bigger area, the channel. Okay. Now so if you try to reduce this, then it is kind of say only you have got only say this much amount of things to go here. So eventually you will see a more delay. So okay, now what is this drive strength? So what is the meaning of this X8? So what is this X8 and is there any link between this length and width and this drive strength?
Sir, we need more width for more like drive it or figure like that. So we required more width to drive more fan out.
Oh, okay. So the question for you is what is drive strength and why do we need them? Okay, that's your homework. Just note it down. What is drive strength and why do we need multiple drive strengths? Okay, now, so let's continue on the W and L. So we talked about W and then L. So we learned that when your L reduces, the delay decreases. So this is kind of on the advantage side. That is why we keep trying to target the new technology and try to see if we can take the benefit of more performance and etc. And now coming to the width. So that width and the technology does not have any relation. Okay, the transistor width is depending on your requirement, you kind of decide. But L is something that depending on the technology. Okay, so your gate length is going to be say kind of 0.028 in case of 28 nanometer and zero point zero 0.04 in case of 40 nanometer and then point 0.1 zero point 0.016 in case of 16 nanometer. Okay, so we talked about multiple, basically the drive strengths. Now, so there is another homework that I wanted to give you. That is, what is multi-channel library? multi-channel. Multi-channel, what is the meaning of multi-channel? Okay, what is the meaning of multi-channel? Okay, now remember, to achieve your PPA, you know what, the best, in case if you want to achieve the best QR, you know what, you need multi VT library, which we would cover in the upcoming classes, and you also need multi-channel library. Okay, so that you can optimize your design with accurate, or probably with a better PPA QR. Okay, so that is your homework. We would be covering it, but when you get time, just go through it. It should help ideally. Okay, now when we say the gate oxide, what material that we use? What
So
material we
silicon
use?
dioxide.
So it is basically SiO2. Okay, that is what we call it as kind of gate oxide, silicon dioxide. And so you guys have to understand, since we are actually getting into more on the CMOS level and then devices level. So any device that you have, so basically you need to know the basics of RNC informations. Okay. So what is this R? How this R is calculated, and then how this capacitance is calculated. Okay. So this is your C and this is your R. Now how this R is calculated, what is the formula?
Rho L
So
by
it
R.
is, yeah. So it is basically you have, say, a shape, something like this. Okay. Now, if what would be the resistance of this shape? So it is basically R is equal to rho L by A. Now, when you say A, L, what is the L over here? So it is basically the length. So this is your length, and your A is nothing but your cross sectional area. Okay, your cross sectional area. Okay, so don't think that your metal area, it is basically your cross sectional area. Now, the reason why I am trying to spend some time on this is it's going to be very, very important when it comes to your routing. So routing is one of the stage in the physical design flow, and we follow, there are certain things. Okay, one is kind of, we call it like kind of say default rule, and then non-default rule. Okay, default rule and then non-default rule. So you should definitely know how this resistance is calculated, what it, what parameters, it is kind of, playing a major role in calculating that resistance and all of that. Okay, and then now moving to this one, capacitance. So what is this capacitance formula? So remember, what is the basic capacitance definition?
The amount of charge and
Q is equal to CV.
No, so it is a simple thing. Maybe you can call it as a book definition. So it is two parallel, two metal plates separated by a dielectric.
dielectric.
Okay.
Okay, so a simple definition. I'm not complicating things here. Okay, so it is a simple cap definition. It's basically, it's a two parallel plates. Okay, so this is a kind of one plate and this is a kind of one plate, where kind of separated by a dielectric. Okay, when I say dielectric, it could be some oxide or some kind of insulating material, and it can be anything. Okay, so now that, so epsilon A by D.
D.
Okay, epsilon A by D. Now when you see here, it is a kind of area. Okay, and then the D is distance between your plates. Okay, so this d is basically the distance between your plates. Okay, now remember this. So this R and C values, okay, if you look at R and C values, you will end up in talking almost every day when you get into PD world. Okay, so the net delay. Okay, so now a simple thing. So we talked about something like kind of say cell delays. Okay, so now say this is your flip flop. Say this is D and say this is Q. Now just say this. Okay. Now, if you look at, say, this is something that we call it as a path. Now, here we have to kind of divide it in two ways. One is basically this is we call it as a net delay. Okay, so this is net. Now, this particular portion is called cell delay, and this particular thing is again a net delay. Okay, and this particular thing is called again a cell delay. Okay, now your net delay, how the tool calculates your net delay. So when we say it's the kind of amount of time it takes for the data to reach from here to here, that is how we calculate it. So this comes under STA, static timing analysis. Okay, and so in this case we would actually need to know how the net delay is calculated. So now you know R and C of the net that is kind of routed. So now tau equal to RC. This is the kind of formula that we will have it to calculate your net delay. Okay, so tau is equal to RC. That is the basic formula for calculating your net delay. So you should know what is the basics of or how the resistance is calculated, and then how your capacitance is calculated. Okay, and then with that formula the tool calculates automatically the net delay. Any questions, doubts? Okay, all right, now moving on to the next one. Okay, what are the different modes of operation? So when we say MOSFET, or basically the MOS, there are three modes of operations. One is basically a cutoff mode, where the transistor is kind of in off condition, and then you have something called linear mode or active mode. Okay, now that is something we call it as a kind of the transistor is said to be in on condition, but it is something that not satisfied this condition, so it is not in the saturation. Now the final one is something called saturation, where the transistor is in on condition, and also there is some formula which is or condition that is satisfied. Now that actually we call it as a saturation. Okay, now remember this is a kind of ID formula. You don't need to really mug it up. Okay, because nobody would ask for it. My only thing that I look at is IDS is equal to 0 in cutoff, but in linear and saturation there is some other value. Okay, now let's go and explore more detail. And remember, in case of the in case of the silicon substrate, right, what it is actually happening, what is here, what is this, why are we assuming it to be ground? So there is something called body effect. Okay, there is something called body effect. Now that body effect says the substrate of the silicon is always connected to ground. Now your threshold voltage depends on that. Okay, depends on your substrate potential. Now your threshold voltage changes if the substrate is at different supply voltage other than zero. Okay, that is a basic assumption that we have. So it is basically NMOS body is grounded. And what about PMOS? What if it is a PMOS?
We tied to power, sir.
We tied to VDD. Okay. Now, see, now you need to understand that during the cutoff, the ID is basically the drain current. It is basically zero. Now, during the linear, the IDS is some value. And saturation, it is going to be kind of current constant. Okay. Now, let's go and understand how the physical changes when it comes to the cutoff. Okay, now assuming you look at this, there is no channel, so this is a kind of p-type body, and this p-type body is basically grounded now. Okay, and then also if you look at here, there is no channel. Okay, so there is no channel. Okay, because you are not supplying anything, so your VG is at zero. Okay, so the transistor is said to be in cutoff. When how this channel is going to be formed, now when your gate voltage is more than something called threshold voltage, then the channel is kind of getting formed, and then that during that time the charges kind of travels. So now in this case during the cutoff there is no channel. And when you say p-type material, what it is, kind of major and minor, what is major
P-type
carrier?
holes are the major ones.
Okay,
Electrons are minor
holes
ones.
are the major one, and minor is
Electrons.
electrons. Okay, in case of N type,
Electrons are major, holes are minor ones.
so electrons are major. Okay, and minor, it is going to be
Holes.
holes. Okay, now having said that, now you see here, this is kind of all of them are kind of holes. So P type, and you see only holes. Okay, now when this is how the scenario, this is how it looks in case of cutoff. Now, when it comes to the linear or active, so you supply, you kind of provide some supply. Okay. Now, what actually happens is the channel is kind of formed by pushing the holes down. Okay. Now, this is the kind of channel that is actually getting formed. Now, the charges that travels, and then that is how your drain potential kind of increases. So now, what is the formula or probably condition for your cutoff? What is the condition for your cutoff? Any idea?
So gate supply should be less than the
Vg is less than Vt.
VT.
Okay, that is your cutoff. Now here Vg is basically greater than
threshold.
Vt.
Threshold voltage.
Okay, and your Vds, it is less Vgs minus Vt. So this is the condition for your transistor is said to be in active mode. Okay, now if you look
When
at here, it's kind of
signal
channel is formed and the charges are kind of moving on. Okay, now it is, we call it as a kind of linear resistor. Okay, now when it comes to cutoff, when it comes to cutoff, what actually happens is there is something called, saturation. Now what is this meaning is the channel gets pinched off at some point of time. The channel gets pinched off and your flow of the basically the drain current becomes a constant. Okay, so now if you look at here, so channel, in the case of saturation, the channel gets pinches off and then your drain current is independent of your drain voltage, and this we call it as a kind of, say, current is saturated, so it doesn't increase anymore, and it is something we call it as a kind of, say, current source. Okay, now what is the condition here? So Vg is greater than Vt, and then Vds
is
is
greater than VGS.
Vgs minus Vt. So when it is less than Vgs minus Vt, it is said to be in linear mode.
Near more.
Okay, when it is greater than, then it is kind of, we call it saturation mode. Okay, now so these three are the modes of operation, ideally speaking. Okay, and whatever that we have discussed uh, is meant for NMOS. Okay, now so if you try to explain NMOS, that is going to be good enough. Okay, so you don't need to worry about your PMOS and all of that. Okay, now so when someone asks you to explain the MOS, okay, it is always important to discuss the IV characteristics as well. Now remember, so here this is something we call it as ID, and this is something we call it as a VDS. Okay, now when you say ID, right? What is the meaning of, what is the value of ID in cutoff?
Zero, sir.
So ID is basically zero. So now your ID is going to be here. Okay, it is as approximately kind of, say, zero. Okay, and now we also talked about active region, right? We also have talked about something called active region. Now remember, in active region, both ID, okay, both ID and VDS increases. Okay, increases. Now that means this is your kind of active region. Okay, now what is this meaning is, in this you see it's kind of your VD is also increasing and your ID is also kind of increasing. Okay. All right. Now this portion, or this is the kind of area where we say it is kind of active. So this is something we call it as a linear resistor. Linear resistor. Okay. Now the next one is kind of say saturation. Now in saturation, what is the condition? Your channel gets pinched off, and then your IDS is independent of your VDS. Now your ID is kind of constant; it doesn't increase anymore. So even if your VDS is increasing, your the value of ID is kind of say constant. Okay, so though your VDS is increasing, okay, from 4 volt to whatever the value is, but your ID is kind of becoming a constant. Now this is something we call it as a the drain current in the saturation. So it is kind of constant, and that is the reason we say this is kind of say saturation region. Okay, so sometimes people would ask you to explain the basics of MOS. So when you are explaining, you need to explain all these three modes of operations, and along with this kind of you know uh, diagram. So this kind of diagram would actually help you even if your explanation is kind of wrong. So but your diagram will give them a kind of more clarity. So there are high chances that you would be shortlisted. Okay. Now, so that is one. And the second is the ID. What is the ID value? So you don't need to really mug up the bigger equations and all of that. You just have to make sure you are kind of, just know what it is under the conditions for each of the mode. Okay. Under the conditions for each of the mode. Okay. And then your IV characteristics. Okay, so this is something that you should be able to explain. Without this, you will not be able to clear any kind of interview. So if you look at, right, we have not covered any kind of equation here. It is just certain conditions. So this equations, yes, you have to mug it up. Okay, but I hit it. So it's since I've been teaching quite long. So this were this formula and all of these conditions and all I remember it. So yeah. Okay, so these are all the basic things of MOSFET. If someone asks, you should be able to explain all these basics. Okay, so any questions here? Okay, now let's move to the next topic. Okay, so next, so the subthreshold, the second order effects, we will cover it little later. And what we will do is we will try to cover the power dissipation and then basics of CMOS inverter for today. Okay, and then we will drop for the day. Okay, so let's take a short break and then we will come back and we will discuss on the power dissipation and then what is CMOS inverter and all of that. Okay, we'll take a short break. So time is 8:05 and let's meet at 8:15.